So just really briefly going to go over the different signal detections that you get with your enzyme conjugates, just because I think they're quite important to understand the differences so that maybe if you're seeing high background with one, you can change to the other. So this was the original ABC complex. And so what this is an avidin biotin complex. And so what happens here is that you use your biotin labeled secondary, and then your avidin biotin forms a tetrameric protein, which is this for here, but then this also binds 4 others and creates this enormous signal complex. So this is highly sensitive and gives really strong signal amplification. However, it is a large signal complex and can diffuse poorly in certain tissues, and things such as brain has actually high endogenous biotin levels and can bind to highly glycosylated proteins like avidin. So when you're looking at glycosylated proteins in this system used to cause high background. So now what is typically used, and if you're looking at an ABC method, it will actually probably be this labeled streptavidin method instead. So instead, we're using streptavidin, and this just forms a singular tetrameric protein that doesn't bind to others, and it's not glycosylated. And so therefore, you're going to get lower background and also has better tissue penetration because it has this smaller size here. But what we typically recommend at Protein Tech is that we use our HRP polymer detection method. And so we have an HRP polymer secondary, and this is better because, as I mentioned, endogenous biotin from the ABC methods. So biotin is using the ABC method, and endogenous biotin in certain tissues, such as the brain and with frozen sections, can cause high background. So this polymer technology can eliminate this, but you also get really good signal amplification and also good tissue penetration because it is smaller than the ABC method, and also less tendency to aggregate. So you're going to get improved signal because you're not going to get this high background from aggregation of your secondary. So as well as chromogenic, we also have our fluorescence signal detection. So with your fluorescence signal detection, we have a fluorophore conjugate. So here you have your secondary or your primary antibody, which can be conjugated with a fluorophore. And typically fluorophores are excellent if you're multiplexing proteins of different abundance because they have this, have this ability to look at tissues with a wide dynamic range of abundance as well. So you can see small abundant proteins and large abundant proteins in the same sample. You can also image thicker tissues when using a confocal microscope because you're able to Z-stack your tissues using this. Z-stack through the tissue and then flatten it, and you get a much higher resolution than if you're just using a snapshot, for example. And in terms of the fluorophores, we have our conventional fluorophores, so things such as FITC, or we have our synthetic fluorophores, so things such as the popular Elexaflor, or our proprietary dye, Coralite. And the problem with FITC is that it's been around for a really long time, and it's a really great dye. However, it can bleach quite easily and can be more unstable than the synthetic dyes such as Coralite. And the synthetic dyes are really bright and very stable, and also are less pH sensitive as well. So these are typically more used for confocal detection now. So these are just some differences between fluorescence and chromogenic. So fluorescence, as I said, really easy multiplexing, high dynamic range and target co-localization. However, chromogenic, because it acts by precipitating the substrate, this means that you're going to have a longer lasting signal. Essentially, your signal will be there on the slides forever, whereas understandably, the signal fades due to the quenching and bleaching of your fluorophore. Chromogenic is more highly sensitive, so you will be able to detect lower abundant targets, and also easier imaging. You don't need any fancy microscope in order to do this. You can just use your bright field microscope. So as well, I want to talk to you a little bit about going direct or indirect. So direct means simply where you have your fluorophore directly conjugated to your primary antibody. And these are really good because you're going to get less background because you're not going to have any non-specific binding from your secondary antibody. So this also means you're going to get high resolution, but also one of the benefits is that you will have a shorter protocol. When using just a singular direct antibody, you don't have to have further washing steps and incubation steps with your secondary. One of the disadvantages of going direct, though, is that you will limit your multiplexing flexibility because you only have this target with that color. And indirect is also good because it amplifies the signal because you're going to have 2, 3, 4 secondary antibodies binding one primary antibody, causing this signal amplification. So going direct is best if you have a high abundant target. So at Protein Tech, we've recently launched our new range of our Coralite antibodies. And these are incredibly popular, and these are directly conjugated primary antibodies for easy multiplexing. And so we have stringently validated these, ensuring reliable results. We also get really crisp images with low background because, like I said, you're not going to have any off-target binding by your secondary antibody. And these are perfect for high abundant targets, but you don't need signal amplification by going indirect. And we have 4 colours in our Coralite dyes. So these are 488, 594, and 647. And these are our proprietary synthetic dye, which is equivalent to the Alexa flaws in spectral profile, brightness, and stability.